Sigueu tots benvinguts a aquest acte acadèmic d'investidura del professor Alessio Figalli, com a doctor honoris causa per la Universitat Politècnica de Catalunya. Una cordial salutació també per a aquells que esteu seguint aquest acte a través del canal UPC Televisió. M'acompanyen a la taula la secretària general de l'UPC, doctora Margarida Espona, i el vicerrector de Política Internacional, el professor Juan Jesús Pérez. Tinc el plaer d'obrir la sessió. La secretària general de la Universitat Politècnica de Catalunya, doctora Margarida Espona, llegirà l'acte de nomenament del professor Alessio Figalli, com a doctor honoris causa d'aquesta universitat.
Avui, 22 de novembre de 2019, en aquesta cerimònia solemne que ens aplega, celebrem l'acte d'investidura com a doctor honoris causa del professor Alessio Figalli, acte amb el qual tenim l'honor que s'incorpori com a membre de la nostra universitat. Com a secretària general, certifico que el 24 de maig de 2019 el Consell de Govern de la Universitat Politècnica de Catalunya, per mitjà de l'acord CG 2019-03-17, va aprovar nomenar doctor honoris causa d'aquesta universitat el professor Alessio Figalli, a proposta de la Facultat de Matemàtiques i Estadística de la UPC i amb els vots unànimes de tots els membres del Consell de Govern. És, per tant, un honor i un plaer celebrar aquest acte d'investidura del professor Alessio Figalli com a doctor honoris causa de la Universitat Politècnica de Catalunya. It is an honor and a pleasure to bear witness to this award and to be able to personally congratulate Professor Alessio Figalli. È un onore e un piacere essere testimoni di questo prestigioso riconoscimento e potermi congratulare personalmente con il professor Alessio Figalli.
Gràcies. Prego el professor Juan Jesús Pérez, vicerrector de Política Internacional de la Universitat Politècnica de Catalunya, que vagi a buscar el professor Alessio Figalli. Prego el padrí, Francesc Cabré, que faci la laudatio dels mèrits.
Dear Rector, members of the Executive Council, UPC School Directors, dear Professor Figalli, I'm extremely pleased that my university is conferring the doctorate honoris causa to Alessio Figalli, following an initiative of the Dean of the Facultad de Matemàticas y Estadística. I'm pleased not just because of Figalli's relevance within mathematics, but also because of my scientific relationship with him and his important mentoring of former UPC students. It is an honor for me to introduce him to you by briefly explaining his trajectory and contributions. Alessio Figalli is a 35-year-old Italian mathematician. He was born in Rome in 1984. From 2002 to 2006, he was an undergraduate student of mathematics at the Scuola Normale Superiore di Pisa. He obtained his PhD in 2007 at the age of 23, under the supervision of two great mathematicians. At the Scuola Normale, Luigi Ambrosio, Fermat Prize and Balzan Prize, and at the École Normale Supérieure de Lyon, Cédric Villani, Fields Medalist. Within mathematics, his area of research is analysis, more precisely partial differential equations and the calculus of variations. I will briefly talk about these areas at the end of my speech. After his PhD, Figalli spent 2 years in France with permanent positions already at the Université de Nice and the École Polytechnique de Paris. He then moved to the University of Texas at Austin, where he has spent most of his career, from 2009 to 2016. He started as associate professor and Harrington faculty fellow, and later became full professor and holder of the R.L. Moore Chair. Since 2016, he's been full professor and holder of a chair at the ETH in Zurich, Switzerland. He has mentored about 10 PhD students and 10 postdocs. He's currently editor of 9 mathematical journals. He has published about 150 articles, a very large amount for a mathematician of his age, with about 90 collaborators. I admire a particular feature of his scientific production, the incredibly large spectrum of topics and areas in which he publishes at the highest level. In 2012, Figalli received an important prize, the European Mathematical Society Prize for young researchers aged under 35. In 2018, a year ago, he got the top distinction in math. He won the Fields Medal, which was given to him at the International Congress of Mathematics in Rio de Janeiro. This is the most important prize for mathematicians, together with the more recent Abel Prize. Winners of the Fields Medal must be under 40 years old. Alessio Figalli got it at 35. 34. He had another chance, therefore. And he became the second Italian mathematician to get it. Enrico Bombieri was the first in 1974. Italy has produced some of the world's best mathematicians since the 15th century. Among them, Cavalieri, Tartaglia, Torricelli, Riccati, Ricci, Ruffini, Beltrami, among many, many, many others, and Levi, a mathematician whose results I admire a lot. Beppo Levi was Jewish, was an Italian Jewish, and had to emigrate to Rosario, Argentina in the early 30s. There he joined a group that included Lluís Santaló, the most prominent Catalan mathematician ever. The group succeeded in making Argentina a strong country in mathematics in the 20th century. In fact, Lluís Santaló was awarded an honorary doctoral degree by the Universitat Politècnica de Catalunya in 1977. Taking into account that Sir Michael Atiyah got it in 2008 here, we are now celebrating the 3rd honorary doctoral degree awarded to a mathematician in our university. The group that emerged in Argentina from Levi and Santaló gave great mathematicians like Calderón and also Caffarelli, Luis Caffarelli, a professor in Austin, Texas, who was mentor of me and in a way also mentor in the initial steps of Alessio's career in Austin. He's still a professor in Austin, Luis Caffarelli. More recently, many of the top Italian mathematicians have studied at the Scuola Normale Superiore di Pisa, like Figalli. This shows the great importance of having institutions that focus on excellence and on the top best young students. A system largely implemented in countries like France or the USA, for example, but much less so in Spain. In this respect, the Facultad de Matemàtiques i Estadística and the Centre de Formació Interdisciplinar Superior, CEFIS, of the UPC can be proud to have produced some of the best young mathematicians in Spain in recent decades. However, in my opinion, if our country wishes to have a Fields medalist at some point, an even stronger focus on top students must be put, especially at the undergraduate level. I believe that the strongest and more intense undergraduate program focused only on mathematics could be placed for those students who don't want to do a double degree, but just put more strength in mathematics. In recent years, several FME, Facultad de Matemáticas y Estadística, students have won the prize José Luis Rubio de Francia from the Real Sociedad Matemática Española, which is awarded every year to a young mathematician working in Spain. It is one of the most important prizes in mathematics in Spain. Xavier Rosotom and Joaquim Serra, who both took their degree and PhD at the UPC, are some of the recent awardees. Alessio Figalli is responsible for this success. Indeed, he mentored Xavier and Joaquim as postdoctoral researchers in Austin, Texas, and Zurich. This has had a huge impact on their growth as professional mathematicians. All three, Alessio, Joaquim, and Xavier, now live in Zurich and work together very intensively. In addition to what they have already produced in joint works, I know that we will soon be receiving further great scientific news from them. Xavier Fernández Real is another great student who took his undergraduate degree at the UPC. He moved to Austin to do his PhD under the supervision of Alessio Figalli, and he's now completing it in Zurich. Xavier has already published 8 research articles and could have finished his PhD. It is not easy, however, to give up on all that one can learn if one is being trained by Alessio Figalli. We can be very pleased that Fernández Real will add to the list of outstanding mathematicians who took their degree at the UPC. For all this, thanks, Alessio. The impact on the future of Catalan mathematics will be considerable, in my opinion. Let me now explain how I first met Alessio Figalli. The story bears some relation to Ennio De Giorgi, 1928-1996, a professor at the Scuola Normale Superiore di Pisa, and one of the most important mathematicians of the 20th century. Having finished my PhD, I started to work on a famous conjecture by De Giorgi. A conjecture is a statement that some mathematicians believe to be true. Still, under a complete mathematical proof of it is found, the statement could turn out to be false. While I was trying to prove the De Giorgi conjecture in 1995, I had the chance to spend 3 months as a European Union postdoc at the Scuola Normale, and I met De Giorgi in person. I was very impressed. Back then, I was only 29. Meeting him strengthened my will to solve the conjecture. I started working on it with Luigi Ambrosio, a former student of De Giorgi and future PhD supervisor of Alessio. 4 years later, in 1999, Ambrosio and I could solve part of the conjecture. Our article became one of the main topics in Figalli's tesi di laurea, his undergraduate thesis. I remember receiving several emails from student Alessio Figalli, quoted. The emails clearly showed maturity. I was impressed when he pointed out that in our paper, one mathematical claim needed some more justification. It was a very subtle point, difficult to detect by an undergraduate student, even by professional mathematicians. We were all happy finding out that there was a quick and precise justification of the claim. The following is a much more recent interaction and I believe a beautiful story. After my 3 months in Pisa in 1995, I moved to Paris for a postdoc, European Union postdoc. There I worked with an important French mathematician, Haïm Brezis. At that time, he was very interested in a problem that captured my attention. The problem turned out to be very difficult to solve and became a conjecture. We could call it the Brezis conjecture. I worked on it from then on, 1995, and published several partial developments. In 2013, I made important progress, but that still did not solve the conjecture. 3 years ago, I went to Zurich and explained the conjecture and progresses on it to Alessio Figalli. He was captivated by its beauty, and we worked intensively for a week, but still we could not solve it. After that, I discussed the plan with several very prominent mathematicians in the field at several top institutions, again without success. A year ago, I returned to Zurich for a great conference that Alessio Figalli, Joaquim Serra, and Xavier Rosoton organized at the ETH. I asked them to meet at ETH, this time all 4 of us, to give the Brésis conjecture one more try. Joaquim Serra and Xavier Rosoton were my PhD students in 2003 and were aware of my progress and had already tried to complete the conjecture together with me. This time we met the 4 of us. They agreed, fortunately, because in 3 days we proved the conjecture. We were very happy, of course. Without them, it probably would not be solved yet. Therefore, many thanks to the 3 of them. It has become a beautiful joint article by the 4 of us, which we finished last July, and for me it represents the culmination of 23 years of work on the problem. As a result, I'm lucky enough to have been doing math with Alessio Figalli intensively over the last year. I have got to know him better mathematically. He has all the aptitudes that a mathematician needs: curiosity, depth, sense of beauty, technical skills, ambition, optimism, and perseverance. Several times I have been astonished by how far and deep, fast he can get from a good idea. He also has a very useful quality, an appropriate measure of being practical, being efficient. This makes me think of something I read on the occasion of his Fields Medal about his childhood. He would do all his homework first to avoid parents' complaints and to be able to fully enjoy playing with other kids afterwards. This is efficiency. He's still like that. Doing math with him is a joy. One just keeps learning and learning. At the same time, as a person, he's easy, nice, friendly, uncomplicated. He just makes things simple and with no pain. Later on, Professor Figalli will present some details about his research area. I will therefore be brief, but I would like, in any case, to say a few words about it. First of all, we should be aware that almost all scientific and technological issues in modern life have some mathematics behind them. Second, very often, and still today, such mathematics are highly non-trivial, often, or are simply not available yet, and several decades, at least, may be needed for them to be developed, to be understood. This requires the work of mathematicians themselves, but also their interaction with physicists, engineers, chemists, etc. In addition to these disciplines, traditionally more mathematically oriented, physics, engineering, chemistry, others such as biology, sociology, financial investing, big data, the World Wide Web, are demanding more new mathematics. We therefore have lots of work to do, and we are happy about it. Alessio Figalli's field of research is partial differential equations, traditionally called the equations of mathematical physics. The most famous ones are the heat equation, think of a reactor, or of ice melting in water. The wave equation, think of an auditorium, or a Wi-Fi network, or how to find out through waves if there is oil underground. The heat equation, the wave equation, and the equations of fluids, Think of ocean streams or of weather prediction. It is usually impossible to write the exact solution to these equations for a concrete body or situation. It is thus of great importance to learn qualitatively and quantitatively about the essential properties of their solutions. In partial differential equations, this requires the use of many sophisticated mathematical tools. Once and only once their essential properties are understood, we will be able to compute the solution in concrete situations through numerical methods with the aid of computers. This will work most of the time only after an essential analytical comprehension of the problem in partial differential equation. Note that one often needs more than 3 variables to describe three-dimensional objects. For instance, Newton's equations to describe the movement of one planet involve 6 dimensions, 3 positions and 3 velocities or momenta, plus time, 7. The Bressis conjecture that we solved last year claimed that up to 9 dimensions, the observable stationary solutions of certain heat equations are always regular. That is, nice, smooth, without singularities, and hence easier to compute. Since 1975, we had known that this fact was not true for 10 dimensions and more. It has been 44 years since 1975 when the problem was first studied. The 2018 Fields Medal citation for Alessio Figalli reads, "For contributions to the theory of optimal transport and its applications in partial differential equations, metric geometry, and probability." Indeed, Figalli discovered that the theory of optimal transport has enormous applications to presumably unrelated phenomena, such as to some equations in mathematical physics, for instance, those modeling liquid crystal screens, to mention but one. He will explain to us what optimal transport or optimal allocation of resources is, as formalized by the French mathematician Gaspard Monge in 1781. Let me just introduce it with an example. Think of a big hole in a garden and a pile of exactly the right amount of soil to fill the hole. I'm responsible for choosing which portions of soil are to be moved to which portions of the hole. Knowing that this is going to be an exhausting physical task for me, and I do not want to be too tired at the end of my day of gardening. I may initially try to save energy by moving the soil closest to the hole to the part of the hole that is closest to the soil. This will, however, make me work harder later on, moving the farthest soil to the farthest parts of the hole. The problem is therefore, what is the most economical way of transporting the soil, in the sense of which part of the soil must be brought to which part of the hole to minimize the total amount of work done. It turns out that this is an extremely rich mathematical problem that took several centuries to be understood. It was only fully solved and understood a few years ago. Let me mention 3 of Alessio Figalli's most relevant contributions. The first one is on the regularity of transport maps. Figalli and Guido de Filippis, in a paper in Invenciones Matematicae, 2013, got a striking result that had remained open since Luis Caffarelli's fundamentals results in the 90s. It establishes regularity for the Monge-Ampère equation, which is behind the optimal transport map, when the right-hand side is just measurable. This is for mathematicians. A second breakthrough contribution is in the theory of free boundary problems. Here, for ice melting in water, one might wonder how regular the contact surface between ice and water, which evolves over time, is. In a paper of Figalli's, written in collaboration with Joaquim Serra, Invenciones Matematicae 2019, very recent one, therefore, the authors make a breakthrough and largely improve, again, Caffarelli's seminal results from the 80s. A third area in which Figalli's contributions have been fundamental, and which I feel very close, from 2019 onwards, concerns stability issues in geometric inequalities. Since ancient Greece, we know that among regions with equal perimeter, the circle is the one that has the greatest area inside. This is called the isoperimetric inequality or isoperimetric problem. Its proof is just from the 20th century. Quantitative versions of this fact are of great interest. That is, one may like to know how close to a disk a region is, knowing that the relation between perimeter and area for that region is very close to the optimal one given by disks. Figalli's results in this area are numerous and a real revolution in the topic. Finally, through there are many more, let me mention his contributions to the theory of the spectra of random matrices using transport techniques, again, as well as to weak KAM theory in Hamiltonian systems, a topic of interest for our dynamical systems group at the UPC. To finish, let me thank Professor Figalli for accepting the UPC honorary doctoral degree. This is an honor for our university. I also thank you all for your attention and hope that you enjoy this ceremony as much as I am doing.
Doctors, obriu-vos. Anem a investir plenament el professor Alessio Figalli com a doctor honoris causa per la nostra universitat. on behalf of the faculty of the Universitat Politécnica de Catalunya, in recognition of your outstanding achievement, I grant you an honorary doctorate. By the authority vested in me, I present you with this diploma. I also present you with this birretta, a revered emblem of the highest academic level. Wear it proudly as a symbol of your achievement. Receive the ring, traditionally bestowed in this ancient ceremony, as an emblem of the privilege of signing and sealing reports, consultations, and criticisms, corresponding to our science and profession. Also, receive these white gloves. Which signifies that your hands must remain pure and, like the ring, are a symbol of your dignity. Henceforth, you shall form part of our university faculty. Please receive a fraternal embrace from those who are honored to call you a colleague. Please proceed to yours.
Dear Rector, members of the Executive Council, this is called the Rectors, dear professors, dear students, dear staff, dear ladies and gentlemen. It is a great honor for me to receive this doctorate honoris causa from the Universitat Politécnica de Catalunya. Besides, of course, feeling extremely honored for receiving a doctorate honoris causa from such a prestigious university as UPC, as you may have already heard in the speech by Professor Xavier Cabré, you are aware that many mathematicians from UPC had and still have a very important role in my career, and this makes such an event and such an award even more special for me. So, coming back to the story that Professor Cabré mentioned, when I was just a student, 2004 undergraduate student in Scuola Normale in Pisa, I was writing my bachelor thesis on the so-called De Giorgi conjecture. De Giorgi was a very famous Italian mathematician, one of the best mathematicians Italy ever saw. And he was particularly well known for his intuition and his ability to state conjecture that always up to now turned out to be true. And so exactly this intuition brought him to postulate many conjectures, and then this gave a lot of work to mathematicians for decades. Still, they give work to us. And so many mathematicians were challenged by his conjecture, and they tried for many years to attack them. In particular, the conjecture we were referring to before, and is this a famous conjecture stated in 1978 by De Giorgi, and it was relating two very important areas of mathematics. On the one hand, it was connected to the so-called theory of minimal surfaces. So minimal surfaces are surfaces that minimize the area. The idea is that you have a metal wire, you take your metal wire inside soap and this creates a soap film that bounds the metal wire, and the equilibrium shape of this soap film is what we call minimal surfaces. And these are objects that we encounter in nature, and mathematicians have studied them since almost 100 years. On the one hand, there are partial differential equations, PDEs. These are equations that arise in many phenomena, physics, chemistry, biology. Essentially, every phenomenon in life can be described by PDEs. And the De Giorgi conjecture was making a very strong connection between these two fundamental topics. And this conjecture is still open until now, but there have been fundamental contributions. And probably the most relevant contribution known until now, in terms of solving the De Giorgi conjecture, is this result by my former advisor, Luigi Ambrosio, and Xavier Cabré. They have this fundamental paper in 2000 that, my goal as a student was to read it, understand it, and give a presentation of what connected to the whole area of minimal surfaces and give an overview of this subject. And actually, this was the beginning of my interaction with Xavier Cabré, because while reading their paper, I had several questions. So I wrote to him as just a student, and he replied to me. So I was extremely honored to think that Professor Cabré would spend his time to reply to the email to me. And then we got to meet in person a few years later. And in particular, I remember in 2008, I was working in France in École Polytechnique, and I went to Austin for 1 month visiting Luis Caffarelli. And it turned out that that period was the period of his 60th birthday. So many people were around to celebrate his birthday. And one of the people around was Xavier Cabré, who spent, I think, a couple of weeks in Austin during his visit. And so we were together for many days. And in particular, the one connection that we had is that the fact that Professor Cabré, before moving back to Barcelona, was a professor in Austin. So he could share with me his experience during his years in Austin. And I should mention that at that moment, Austin had just made me an offer to move there. So I was 24, was living in France already, which is not Italy, already changed my country. And I had to decide whether to move to Texas or not. And it's a big change in life. So I was hesitating, and I had several discussions with Xavier, who told me all the good side of Austin, both as a city and also as for the math department. And so, for sure, the fact that I could interact with him, a person who had no interest to tell me anything wrong, just was sharing his view, was fundamental, because then I made the decision to go, and clearly has been one of the most important decisions of my career, because what I'm now is definitely because I passed through Austin. So actually, I'm very grateful to Professor Cabré for this. So then the interactions were not ended, even transversal in some sense, because another, let's say, gift gave me was that in 2014 I had these two brilliant PhD students who graduated, so Xavier Rossoton and Joachim Serra. And at that moment, Xavier Rossoton was applying for postdocs, and he made him come to Austin. I mean, encouraged him to go to Austin. And so this was the beginning of our interaction. And we worked for all the period that we were together in Austin, we worked together. And then 2 years, in 2016, I moved to Zurich. And that was the moment where Joachim Serra was looking for postdocs. And I was more than happy then to take Joachim. And this was the beginning of another great interaction with him. And then also, it turned out that also Xavier Rossoton moved to Zurich. That's dependent on me. And now the three of us are in Zurich. And we have been working together intensively in the last 2 years. And I should say, so thank you for bringing them to work with me. And in addition to this, he already mentioned that, but there is another student from UPC. He was a bachelor student, and then he started again the PhD with me. So it was again through Xavier Cabré that he started. So I have now a PhD student from UPC, Xavier Fernandez Real, who is gonna graduate from Zurich this year. So as you can see, I had many interaction with mathematicians and I had many students, but the interaction with mathematicians from UPC has been very intense for me and very important. And then this interaction now probably is culminated with the recent result that Xavier already mentioned in his speech about the solving this Bresis conjecture. This has been 23 years of his work, and we are extremely happy, both me, Joachim Serra, and Xavier Sottono, having been part of this wonderful project. So I think this is a nice story, very positive ending. And so this story shows, I hope, to you why receiving an honoris causa is an honor and a prestige, but having it from UPC is even more special. Now, this is a celebration of interaction with the university, but it's also a celebration for mathematics. So mathematics is a very dynamic subject, and it has applications in everywhere, in everyday life. And in fact, maybe people don't always recognize it as they should, but more and more, I think we will see a clear application of mathematics in the modern society, even if they're already there, but they will be more and more evident. And just to mention clear application that are already present, you should just think of recording devices, computers, artificial intelligence, cryptography. All these will not exist. And in my case, I worked on several topics, but one which has been always very important for me is optimal transport. So I will use support of some slides just to give you a brief overview of what optimal transport is. I want to make very simple, but just at least describe the problem. So the origin of optimal transport dates back to the end of the 18th century. So the paper of Gaspard Monge, Mémoire sur la théorie des déblais de Ramblay, dates back to 1781. And so the goal of Monge in his case was to find the cheapest way of transporting material from one place to another. And actually, it's due to these studies that Napoleon used the support of Monge during his campaign in Europe in order to use this theory for military application to build fortifications. So Monge made really important contributions, but for some reason, I don't know why, but that's history, this problem was then forgot for many, many years. And it's only in the 1940s then Leonid Kantorovich, a Russian mathematician and economist, kind of restarted working on this problem. And he made fundamental contributions. So let me just show you first this Monge problem. He wanted to extract material from the ground and build fortification. And so when you talk about optimal transport, you should always specify what does it mean to be optimal with respect to which cost, what is the optimality. So for Monge, in his interpretation, he decided that the natural notion of cost is the traveled distance, which means that if I want to move material I don't know, from Barcelona to Madrid, it's 800 kilometers, so I pay 800. And then if I want to move it from Barcelona to Girona, it's probably 100. So it's proportional to the number of kilometers. And this was the beginning of the story. And then Kantorovich came. So here is Leonid Kantorovich. He got the Nobel Prize in Economics for his studies for his contribution to optimal transport. And so Kantorovich really set the basis to understand mathematically this problem. And this picture that you see there is just to give a very simplified version of Kantorovich's interpretation of the problem, where you see the bakeries, the square, and the circles are the coffee shops. So let's say each bakery produces a certain amount of bread. The coffee shops are asking for some bread. And let's say, for instance, if you look by, oh no, the pointer is, back. Oops. Okay, let's do this. Sorry. I think they are, okay, I'm not, okay. You see, for example, that bakery on the top corner, it produces some amount of bread, let's say 10 kilograms. And then there are the coffee shops nearby who only need each of them 4. So maybe we'll send 4 kilograms to one, 4 kilograms to another one, and then the third one, it can only send 2 kilograms because that's what is left. So the next bakery maybe, the next coffee shop say, okay, I got 2 kilograms, I still need 2 more. I will need to use another bakery to get more bread, and so on. So this becomes kind of a combinatorial problem where you need to introduce arrows to decide which bakery will furnish bread to which coffee shop. And then for each arrow, you should say how many kilograms are gonna go along that arrow. So you have to set up this mathematically. And this is a bit different from Monge. So Monge was not able really to take this problem with this theory. And he introduced a very solid mathematical theory that has been at the basis of many optimization problems. And this is why Kantorovich became so famous. So he really developed the big mathematical behind this. Now, going on, instead to go for mathematics, we had to wait much more. So to really look at the current mathematical world, we had to reach the 1980s. So in particular, the more important results in that period were by Renier and Rachel and Ruschendorf. And essentially what they formulated the mathematical problem very cleanly, right? So the idea is that you have a cost function, Cxy now, it's not just the distance. And for any cost function, you want to solve this minimization problem. And you have many questions. For instance, does a Tolkian transport exist? Can we understand how it looks like? But now, independent of this, what really made mathematicians fascinated by this problem is the fact that this problem had connection to other areas. So it was not only a problem by itself, interesting by itself, but also it was able to tackle problems in other areas that no one knew how to attack before. And in my case, actually, I have 2 personal experiences that I would like to share. But before that, I would like to show you one explanation of the standard question of why I got the Fields Medal. So this is the explanation that was given by Ortolani, wrote a comics, and la scuola normale. So I got the Fields Medal for my contribution, and you can see that I got caught by the police traveling without ticket. So the solution to move cheaply is like go without paying the ticket until they catch you. So be sure they catch you after you get the Fields Medal. Then you're fine. Anyhow, so going back to my side of mathematics, actually, Xavier Cabré already mentioned this isoperimetric problem. So the problem of minimizing the, let's say, you want to fix the volume of your object, like an object, let's say a shape in the plane of area 1, and you want to find a shape which has the least possible perimeter. This is a very classical problem which is connected to many phenomena, and we see that, for instance, in soap bubbles. So soap bubbles is the 3-dimensional version of this question, because when you play with soap bubbles, what you do is that you blow air inside the bubble closes up when it detaches from the plastic ring, and the moment it detaches, air cannot go in and cannot go out. So the amount of air inside the soap bubble is fixed, and then the surface tension, because this is due to the soap molecular tension, immediately acts as an energy and wants to make the bubble round, because the round is the cheapest possible shape, is the shape that minimizes the area. Nature wants to minimize. There was this minimization principle behind nature, behind stable thing that we observe. And so that's why it becomes immediately round, because it's a solution to the isoperimetric problem. So in my case, I actually was interested in something a bit more general than that. So in 1878, Gibbs understood that not only droplets, but also crystal arrange themselves that according to a shape that has the lowest surface energy. So soap bubbles want to be round, and crystal want to have some structure, some shape, which depends on the intrinsic molecular structure. So this means that it's not actually the same energy, otherwise they would be all round. But provided you modify suitably the formulas, you can describe soap bubbles and crystals through the same as the same mathematical object. And this is actually through the work of Wolf, who was a crystallographer, that from 1901 we got the mathematical formulas to describe the surface energy of crystals. And so this means that essentially the crystals we observe in nature have the shape we see because they want to minimize some energy. And now you ask the question of stability. In a sense, suppose that I have forces acting on the crystal, or maybe I raise the temperature and then the crystal gets deformed because of temperature. How this energy that I give to the crystal will change its structure. So as we give energy to this crystal, for instance, by raising temperature, then the crystal will start to change its shape. And the question we have is, based on the amount of energy, can we understand how much the shape will change? So let's say that I call epsilon the amount of energy, then I raise my temperature a little bit, so it's not much, but so that it gets deformed, not too much. You see the shape on the right. And now optimal transport kicks in. Why? Because we can think on optimal transport as kind of a way to understand how each molecules move along this heating process. And so I have this transport map that is moving the molecules from the initial crystal to the final crystal. And then through this map, I can try to understand the shape problem. This is how we can think about it. And very informally. And then through this method, that's what we proved in 2010 with Francesco Maggi and Aldo Pratelli, was that the shape of the crystal can change at most by square root epsilon. This was a long-standing open problem because people could not get this bound with this precise power, epsilon to the 1/2. And what was, let's say, important in this result also is that we got a bound which was universal. For crystals, so bubbles, it didn't matter to us. We got a bound that was applying to all the shapes at the same time. But then, of course, mathematicians are difficult to please sometimes. And so I always kept wondering, like, okay, it's true that the crystal has this is the answer, but I never saw a crystal so wiggly in my life. So maybe this is the best you can prove for a general problem where you for you crystals and so bubbles are part of the same problem, let's say. But the moment you say, okay, but now I want to work only on crystals, so bubbles, no, not anymore. So crystals are very rigid objects usually. I see very rigid shape. So is there something we can say as mathematician? Can we really predict what we see in nature? You will never see that in nature. And that's actually something I did this year with He Zhang, a postdoc at ETH, where we proved that the crystalline structure cannot change, which means that from left to right, the crystal has changed a bit, even it doesn't say too much. The only thing that has happened is that maybe some sides of the crystal have been translated a little, but that's the only thing that can happen. There is nothing else. For small energies, this is the only phenomenon you will see. So this is, as you can see, a project over many years. It started actually for me in 2007. And then the second project that is very important for me was to use optimal transport in another problem. So this was mentioned also by Xavier Cabré in his speech about this Monge-Ampère, in fact, the meteorology problem, so equation from meteorology and fluids. So another problem I wanted to study is the so-called semi-geostrophic equations. So these are equations that describe large-scale atmospheric flows. And I want to simplify the problem for you and tell you, okay, suppose that you have two clouds, and you look at two clouds at very close by instant of time. So let's say I look at the cloud and then 1 millisecond later. And then clouds are made of many particles. So the only thing I can see when I take a picture is the ensemble of all the points. And then I ask, who went where? So can I, by just looking at the point on the left and point on the right, know each point on the left to which point it corresponds in the right picture? Maybe, okay, if I draw only a few points right there, you can guess which one makes sense. But if I give you 1 billion points and I ask you, can you pair them, it's more difficult. And then it turns out that the solution is given by optimal transport. So Mike Allen realized this from a kind of a physical viewpoint. So by by looking at the cheapest possible transportation from left to right, you can color each point, and then you get this coupling with points. But this was only not a mathematical proof. It was only an intuition that he could get. He could not really find this in the equation mathematically. It was very difficult to show that. And so this connection was for many years, but some results were lacking, in particular on optimal transport. And we found this tool. We managed to develop this tool with De Filippis in 2013. Well, in fact, a bit before. And then we applied that to solve the semi-geostrophic equation. So, of course, you can see an incongruence in dates. A result in 2013 has been used for a paper in 2012 and 14. This is because in mathematics, usually there is delay in publication. So we did it much before, and then it took some time to be published. But so the technological order, there is no incongruence there. And sometimes when I think about how you solve a mathematical problem, I like to think about this picture where I have a mountain. And my goal is to solve a problem. And solving a problem is like reaching the top of the mountain. I want to reach the top. And the way to reach the top is to try many paths. Because in the years I learned techniques. Each of them gives me some way to attack a problem. And I don't know which one is going to lead me to the top. And then I try. And most likely I will get stuck many, many times. And so maybe I get stuck on the bottom. I get stuck maybe halfway. And then the question is, what do I do? Sometimes you need persistence in the sense that you are maybe on the right point, the right track, just you didn't get the tool needed. And so maybe in few months or few years, you get to get a bit higher and higher. But some moment you have to be a bit humble and understand that maybe you were just on the wrong path and you have to accept to go down and start again. And eventually, sometimes you get to the top. That's fantastic. Sometimes, actually, most of the times one doesn't manage to get to the top, but one learns a lot of things just by the process of trying to solve a problem. And perhaps the process has been, the journey sometimes is more important than the distance. So these were two problems that has been extremely important to me. Maybe one more thing I would like to say is that optimal transport is much more than this. We see that now in many, many things. In particular, very recently it appeared in machine learning, finance, and also in image processing. I will not enter into that, but just an image to show you, for instance, in image processing. So you can take colors from one image, the second one, for instance, this fruit on the right, second image here on the bottom. You take the color from them. You look at a problem of transporting color from the right image to the left image. So you have to do this at the level of histograms of color. And so it's a transportation a bit abstract. And then you use this to transfer colors from left to right, and then applying some filters, and you get very interesting images. So this is more just to show some application. There is actually more, because once you are able to transport colors, you can also transport images one to another. And this has been used now in machine learning. When you want to train neural networks to recognize images, you can use optimal transport as a way to measure how much two images are close, and then how much an image is really an image of a dog or is not an image of a dog, and so on. So in this training of a neural network, now optimal transport is also a very useful tool that many people are working on. So I think this is essentially towards the conclusion. So I would just like to emphasize that in recent years, mathematics has been progressing extremely quickly. And in some sense, the mathematics and the progress in society, they go along together, because society and the industry will use mathematics to develop. But on the other hand, the more technology we have, the more questions for mathematicians come. And so it's a very good interaction that we are developing more and more. And also, mathematics is always taught, or often taught, as a pure mathematics and applied mathematics. People ask, are you applied mathematician, pure mathematician? This is a good, let's say, definition within mathematics, but the reality is that none of them will exist without the other. So we need both of them. So applied math needs pure. And that's why it's important to have, also free thinking and allow mathematicians in your pure area to continue work on their subjects. So just to conclude, I think I feel that today is not only a celebration of my research, nor just of my doctoral honoris causa, but for me it's a celebration of all mathematics, and also mathematics at UPC. And I thank very much the University of Polità de Catalunya for honoring me with this doctoral honoris causa. Thank you.
Dear Alessio Figalli, Doctor honoris causa, Vice Rectors, General Secretary, Dean of the School of Mathematics and Statistics, Mr. Xavier Cabré, sponsor, directors, academics, ladies and gentlemen. Yesterday at the school, of Mathematics and Statistics held a magnificent workshop in the honor of Mr. Figalli. Added a highly relevant academic contribution to today's important ceremony. One of yesterday's speakers was Mr. Xavier Rosoton, former student of this school, whom we congratulated recently for the Scientific Research Award he received from the Princess of Girona Foundation. Alessio Figalli's speech, The Beauty of Nature and the Art of Problem Solving, highlights an important idea. Solving problems is not an obligation, it can be seen as an art. When the school and our Institute of Science and Education promote programs that contextualize mathematics, they are seeking an approach to mathematics from practical, sensory, and social perspective. Applied mathematics. If we add speeches by the leading authorities in the field to these experiences, I am sure that we will be proving incentive for new mathematical vocations and ensuring that teachers of this subject enjoy it more and have more points of reference in their practice. Last year, Mr. Figalli was awarded the Fields Medal, the highest distinction in mathematics, Nobel Prize. It is said that it is the greatest honor that can be bestowed on a mathematician. On the back of the medal, Mr. Fields chose to feature the head of Archimedes and the inscription Transire sum pectus undoque potiri, rise above oneself and master the world. Thus, as the rector, I am humbly offered this university's highest accolade and ask that when he goes off to master the world, he keep us in mind. Paraphrasing Figalli's, the more mathematics advances, the more technology are we able to develop. I wish to thank the Dean and all the staff from the School of Mathematics and Statistics, also the sponsor, Xavier Cabré, to make this ceremony possible and to invite Mr. Figalli to keep in touch with our university. We are sure that his young age and vitality will make him a guiding light for all our students. With the award of the honorary doctoral degree, this university becomes his home, and his achievements will be especially celebrated here. A final idea from his speech: sometimes the journey is more important than the destination. We wish you a very successful journey. Thank you.